let's begin here, you guys, and see what IB is on the IB syllabus in terms of what we're going to talk about today. First thing is that they expect you to be able to define electric current and define resistance. I hope by this point you've started to recognize that in the IB syllabus, if it says define something, you need to spend some time figuring out what it means, right? Because there'll usually be some kind of a question, either multiple choice that says what is the definition of resistance, or on the written part sometimes it will say define that. So in the syllabus, when they say define something, take a minute or two to think about what those things are and make sure to focus a little bit of study time in the textbook to find that out. You should be able to apply the equation for resistance in the form R equals rho L over A. We'll talk about that. State Ohm's law, compare ohmic and non-ohmic behavior, derive and apply expressions for electrical power dissipation in resistors, and solve problems involving potential difference, current, and resistance. That's hopefully what we will be able to cover today. But before we do that, we're going to travel back in time. We've got to go back about 211 years, more or less, okay? We're going back to Italy, the late 1700s, early 1800s. Imagine that. Renaissance is happening, people are learning all sorts of great things. There's art, there's science, it's beautiful. And these two guys come along and change the world, okay? Luigi Galvani and Alessandro Volta. Excellent, okay? Both of them were scientists, both of them were professors. Luigi Galvani was a professor at the University of Bologna. Alessandro Volta was at the University of Pavia. These were like arch rivals, okay? It's kind of like, I don't know how many of you follow college basketball, but it's like Duke and Carolina in college basketball. It's bitter, bitter stuff. Or, I don't know. Yeah, whatever. They hated each other. And Galvani made a discovery. And here's what he did. He took frogs' legs, okay? Big old frogs' legs like they eat in France. Tastes like chicken. And he took two different pieces of metal and he stuck them into the frog's legs. And the leg started to twitch. And he was like, Galvani believed that he had tapped into whatever it is that is the life essence, the thing that keeps us alive. We know like how our bodies work and stuff, but what is that animal essence that separates living from dead? And what Galvani thought is, here he had this dead inanimate frog's leg, and he could take these metal probes and sticking it in the frog's leg, he somehow felt like he was tapping into that animal essence and bringing it back to life by making it twitch. And he's like, oh, this is great. Alessandro Volta, on the other hand, did not believe his theory. Alessandro thought that because he was using two different kinds of metal, there was something electrical going on in that frog's leg causing it to twitch. The problem was, in the 1800s, early 1800s, we're talking like 1800 actually, the beginning of the 1800s, there wasn't a device sensitive enough for Volta to prove his theory. The electroscopes weren't sensitive enough. He didn't have a way of showing that by taking two different metals, you could create an electric current. And so it was just an argument. And a lot of people believed in Galvani, a lot of people believed in Volta, and these guys were arguing back and forth, back and forth, back and forth. Volta set out to disprove Galvani. Both of these guys are still pretty darn famous in the world of electricity. I don't know if you guys have ever dealt with like galvanized steel or galvanized nails in construction. That's this guy, Luigi Galvani. He developed some pretty cool stuff. Volta you've probably heard of before because we talk about voltage and volts all the time. What Volta finally did, he set forth to disprove Galvani, and the way he was able to do it was with a lot of effort and a lot of research and creating this thing right here. He recognized that if he took two different kinds of metal, and what the metals that Volta used were silver and zinc, and he basically made like a stack of pancakes of pieces of silver, zinc, silver, zinc, silver, zinc, and then he would bathe these things in like a saltwater solution, and with a big enough stack, he was able to generate enough electricity that it could be measured. And he was then able to show that, yeah, if you actually did this frog experiment with the same kind of metal, nothing happens. But two different kinds of metal, you can get it to twitch. And basically, it's not animal essence. It's electricity. You're creating electricity. This device, these pictures right here, here's a better picture of it. Okay, these things were quite large, but this was the invention of the battery. Okay, Alessandro Volta created the first electric battery. And this is kind of what they looked like. They weren't AA's and AAA's. They were a couple feet tall and would generate just a little bit of electricity. But this revolutionized the study of electricity. Because prior to this, Remember, we've been talking about static electricity, and that's what people could do. They could charge things up, rub things, and charge them, and charge them, and charge them, and pow, make a big spark, and it was cool. And then they would do it again, pow, make a big spark. You couldn't do anything with it, but it was neat for like demonstrations. With the invention of the battery, however, everything shifted, because now, rather than creating huge voltages and making sparks, you didn't create huge voltages, but you could create continuous flow of electricity. And that allowed us to do things. So this was a big revolution. Again, it happened, I think it was in the year 1800 or in the early 1800s when this was going on, and it started to shift everything into, rather than static electricity, what we now call current electricity. You create electricity that flows with current, like a river. Okay? So electric current, you guys, in order to have electric current, you need to have what's called a circuit. And an electric circuit is basically a closed loop that electric charge flows through. So usually it's a closed loop made by some conducting material so that electrons can flow from one level of potential to another level of potential. So let's look at some examples of electric circuits and not electric circuits, okay? Look at drawing number A over here. Is that light bulb going to light? Por qué? Why not? Not a closed loop. Now, in a battery, you probably have already recognized that there's a positive and a negative terminal. Those positive and negatives have to do with potential. We talked about potential earlier. You have high potential and low potential. That's what the positive and negative is. And on this kind of a battery, the negative terminal is down here. Notice this one, there's no way for the electrons to get from the positive to the negative. There's no closed loop. So no go there. Not going to happen. How about in B? But we have a closed loop. Okay, excellent. You don't have it going where it needs to go. The electron, I mean, this is a loop, sure, but no, it's not going to happen. And in C, yay, we have light, and life is happy and good, because notice now, the electrons can leave that negative terminal. Since they're repelled from the negative, they will go through the light, they'll make light, and then they'll go to the positive terminal where they have a lower potential and life's happy. I want you to think about something here for a second. I just drew the way the electrons will flow from this. They'll flow from the negative to the positive. The weird thing is, when we do electricity, when we draw circuits and stuff like that, we don't draw the electrons flowing that way. We draw electric current going from positive to negative. Okay? Well, theoretically, there's not much difference. I mean, the idea is the same. But back when we started doing electric circuitry and stuff, they didn't really know what it was that was moving. They just knew something was moving. And so but initially, they were always drawing current from positive to negative. We still do that, even though we now know that this is what's called a direct current circuit, or DC circuit, that the electrons flow one direction from the negative to the positive. But it'd be exactly the same as if something positive went from the positive to the negative, and that's just the way we draw it. It's called conventional current. We draw it from positive to negative. Okay. So rather than drawing pictures all the time of like a battery and some wires and a device that's using that electricity to do something like create light, that's kind of fun, but it's going to get old. So we're going to do these schematic diagrams where we'll use symbols to represent things in our electric circuits. This symbol right here represents a battery or some sort of a potential generator, okay? Usually it's going to be a battery when we're talking about a circuit. Notice that the long line is the positive end. Notice how we draw the current going from the positive towards the negative. Again, that's known as conventional current. We really know that the electrons go the other way, but hey, it doesn't really matter which way you draw, because this would be just the same as a positive charge going that way. This symbol right here is not very good. You might have noticed in your data book that there is a whole page of electrical symbols, okay, whole page of them. So they have different symbols for, like, I think IB uses this for a light bulb, this for a potentiometer, okay, and other things like that. What I will usually do, is I'll draw a battery, and I'll draw a squiggly line. This is pretty common for some sort of a device that uses the electricity to do something. Light bulb, iPod, blender, stereo, whatever, okay? So that's what that squiggly line will usually represent. Okay, so here's our analogy. I got 2 buckets of water. One's full and one's empty. This would be like high potential, and this would be like low potential, okay? If I was then to connect the two with a tube, what would happen? It would even out. Water would flow, correct? It would flow from the high potential to the low potential. So that's kind of what happens with electricity. You have high potential and low potential. The electrons want to flow if there's a path for them to do so. If you put something in that path, let's say in this case, we put like a fun, water wheel device, the flow of that water would cause this thing to turn. That's kind of like how the electrons know to go through the light bulb and make light, somewhat. The electrons really are just going from high potential to low potential. Okay, they're just moving. And if there's something in their path that uses that energy, uses that flow, then that's what happens. It's not like they want to go to the light and make light, but the light's in the way, and they got to get through it. And in the process, they're going to make light. People at home hear this too. So this analogy works good. Current will flow for how long? When will current stop flowing in this case? Until they equal out. So in order to keep it flowing continuously, we need somehow to fill up this bucket again, right? And there's so many ways to do that. Batteries are basically doing that using chemicals. But we can also use, the sun and build a dam, and the sun puts the water up high for us, and we take that energy. We can also burn coal and do that. So there's lots of different ways to keep the full bucket full so the electricity keeps flowing. If we don't fill the bucket back up, the electricity will flow for a little while and then be done, okay? Again, this is truly just an analogy. Please don't believe that this is like a perfect match of what's going on, but it gives you an idea of how you can kind of imagine. All right, so let's talk about some terminology and stuff now. So electric current is represented by the letter I. In your equations, whenever you see the letter I, you should be thinking current. Oh, they're talking about current, okay? And basically, you can think of electric current as the flow of electric charge. How fast electric charge is flowing through my circuit. There's a more technical definition that we'll understand when we get into magnetic fields a little bit, which is the force per unit length between parallel current carrying wires. If I have two wires that are carrying current, they will actually exert force on one another, and that is how we've defined the unit of current. But right now you can kind of think of current as just the rate of flow of electric charge. It's measured in a unit that we call an amp, or an ampere, named after André Ampère, the famous French physicist who studied electricity a long time ago. And 1 amp is the equivalent of 1 coulomb of charge passing through the circuit every second. You're watching one point on the circuit. If I have 1 coulomb flowing by every second, I can say I have 1 amp of current. How do we measure amperage? Well, we use a device that's known as an ammeter. And in order to measure the amperage, we must connect our ammeter in series in our circuit, and I'll explain what that means in just a second. Here we have a really simple circuit, a battery and a device. We'll call it a light bulb. If I wanted to measure the current in my circuit, I would use a thing called an ammeter. And in order to make the ammeter work correctly, and this is something that you're expected to know, I have to connect my ammeter in series. And what that means is I connect it so that the current has one path to follow. It goes through the resistor and through my ammeter, one after the other. That's what it means to be connected in series. This is how you measure current. The current has to flow through the ammeter in order for it to work. It doesn't matter where you put it in the circuit. I could put it here, 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 because since there's only one path, the current should be the same throughout the whole path. You can kind of imagine that like if I had a hose filled with ping pong balls, and I'm jamming ping pong balls in one end, they're going to come out the other end at the same rate. And anywhere in that hose, they're going to be moving all at the same rate. So it doesn't matter where I measure it, I'll get the same amperage, okay? If I was to connect my ammeter like this, so that I'm creating a new path, this is called connecting it in parallel, that would be bad. The light bulb would go out, the ammeter would peg on infinity, and it would start getting really hot and maybe blow up, and it would not work, okay? So just because. Ask me that later when we talk about resistance. Let's just talk a little bit about current and what it does to you. If I came up to you with a pair of electrodes and put them up against your skin, and I drew a milliamp of current across your body, you'd start to feel it. It'd start to tingle a little bit, and you'd be like, ooh, that tickles, okay? If I increased it to 5 milliamps, it would start to hurt. You'd be like, ow, and I'd be like, But like a taser? Okay. Here we go. Okay, 10 milliamps starts to cause muscle spasms. Okay, your body works electrically. Remember that your nerves, the things that make your muscles move and the things that you use to memorize stuff, your nerves are electrical in nature. So if an external, and the electricity, the electrical impulse across nerves is very, very small. So, 10 milliamps is enough to cause your muscles to start, spasming, going, and control it. Okay, 15 milliamps. You lose control of your muscles altogether. This is where you start losing bodily functions and stuff like that. It's bad. 70 milliamps. Again, amperage. A little bit of amperage can be very dangerous. If it's through your heart, it will cause serious disruption of your heart and probably be fatal if it lasts for more than 1 second. Okay? So again, amperage is very dangerous. This is what is dangerous. We've talked about voltage. High voltage doesn't have to be dangerous. That Van de Graaff generator, 350,000 volts. And you can sit there and play with it all day, and it tingles, but it doesn't kill you. Okay, it's the amperage that is dangerous. Okay? We've been talking about potential difference, so you guys are already aware of it. It's represented by the letter V. Sometimes we just say voltage. But again, potential difference has to do with work and energy. It's the amount of work per unit charge or the amount of energy per unit charge. You can kind of think of it as how much energy each of the electrons has. High voltage means each individual electron has a whole lot of energy. Okay? So it's a factor in terms of what's going to happen with the current, but in and of itself, it's not necessarily dangerous. Question. Okay. We measure potential difference in this unit called volts. Okay, letter V also, so that's kind of convenient. If you see V in the equation, it means volts, and it's also going to be measured in units that is also V. And 1 volt is a joule per coulomb. We've talked about this previously. Again, joule is a measurement of energy. Coulomb is a measurement of charge. So a voltage tells you how much energy per charge or how much work each of the charges can do. In a circuit, if you want to figure out how much energy gets used in a circuit, you use a thing called a voltmeter. And you place the voltmeter in parallel. It's the opposite of the ammeter. Ammeter you place in series, voltmeter you place in parallel. I'll show you what that looks like in just a moment. So to measure the current through the circuit, I would attach my ammeter in series as part of the path so the current flows through it. If I wanted to measure the voltage, let's draw this. Let's say this is a 9-volt battery. Okay? This is the positive terminal. This is the negative terminal. So as these electrons are flowing along, or as the current's flowing along here, right here, no energy has been used yet. So my electrons, or the charges, would still have 9 volts of potential. The light would be glowing and glowing and glowing, and the weird thing is, right over here, they would have 0 volts of potential. They would have used 9 volts to make that light. In order to measure that, I take my voltmeter and I place it before and after my device to measure the difference in potential from one location to the next. Okay? They don't go through the voltmeter. And here's the reason why. A voltmeter, there's this property with electrical circuits called resistance, which we're about to talk about. A voltmeter ideally has infinite resistance. So the electrons don't want to go that way. Too much resistance. They're not even going to bother taking that path. So it doesn't change anything when I connect it that way. If, however, I was to place my voltmeter in the circuit and it has infinite resistance, it's like it stops the flow. Nothing happens. Your circuit doesn't work. Okay? Your ammeter, on the other hand, has absolutely no resistance. So by putting it in the path, it doesn't change anything. But if I make a new path and put my ammeter in it, I've created a new path with 0 resistance. All the electricity goes this way. None goes this way. The light bulb goes out. The current goes up. It's crazy. Excellent. Now we get to Ohm's law. This is part of what you need to know. This is less of a law than kind of a definition. It was created by this German guy named Georg Simon Ohm, and he recognized there was a relationship between voltage and current. And this is what he came up with. Okay? This is known as Ohm's law. It's a simple equation. I equals V over R. If you think about it, it makes total sense. If you think about it, it makes total sense. Basically, it says that the current that flows through a circuit will be equal to the voltage that is pushing the circuit. Remember, voltage is kind of like the difference in water, how hard the electrons are being pushed. It's kind of like a driving force. So more voltage gives me more current. And then there's this other quality that prevents the current from flowing, and that quality is known as resistance. Okay? R stands for resistance. So the more resistance I have in a circuit, the less current I have. The more voltage I have, the more current I have. And this is where, when we're talking about dangers of electricity, again, it's the current that we're concerned about. So high voltage doesn't necessarily have to be a big deal. It could be high voltage with a little bit of charge, or high voltage with a lot of resistance is no big deal. When you diminish the resistance for a given voltage, you're going to increase the current. This is why you shouldn't blow dry your hair in the bathtub. Okay?
That say, don't knock on other people's lockers.
Okay.
Don't be a
Let's see, with the exception of superconductors, anything that conducts electricity has resistance. Anything that conducts electricity is going to have some amount of resistance. And we can calculate the resistance. There's an equation for it, and this is one that IB wants you to know about. This is an equation that allows us to do it. And it basically says the amount of resistance that something has, let's imagine it's wire right now, trying to carry electricity, is equal to this Greek letter rho, which that's kind of like mu. Remember mu? We talked about the coefficient of friction. Rho is the same thing with resistance. So that's just a number that tells you something about the particular material we're dealing with. So silver has a certain amount of resistance, gold, copper, they all have different resistivities, and that's what this rho is. Yes, it's a Greek letter P, basically, okay? Don't worry too much about that. The thing you should really think about are these two letters, okay? L and A. And if we're dealing with a piece of wire, what this means is that the resistance in that piece of wire is directly proportional to the length of wire, right? The longer the wire, the more resistance it has. That makes some sense because there's more stuff to flow through. It's inversely proportional to the cross-sectional area, okay? If I make my wire thicker, it will have less resistance. And that kind of makes sense too because it's just a bigger path for the electricity to flow through. The other thing to think about, remember that whatever we have, we're going to have all these atoms in here, these nuclei. That is what creates resistance. Okay, hang on one second, Norman. As the electrons, they want to just flow. They want to go through here. But there's stuff in the way. And every time it hits an atom, boom, it slows down a little bit. Hits a nucleus, it has to change its path, change its path, change its path. Every time it collides with or comes close to an atom, it gives it some energy. It's just like a collision with cars that we talked about earlier last semester. It gives it a little bit of energy. These atoms start to oscillate a little bit more, and that is what we experience as heat. This is why wires get hot when electricity flows through them, because of the resistance in them. If they had no resistance, there'd be no heat, be no problem, okay? But most things do have resistance. Anyway, here is the unit that we use to measure resistance, you guys. The unit for resistance is called the ohm, named after ohm, and it looks like a little Greek letter, omega. Omega, and so that is the unit for resistance. And
the easiest way to draw that.
1 ohm is equal to the amount of resistance that would allow 1 amp of current to flow if there were 1 volt of potential difference. That's kind of the definition of the ohm. And what we can do now is if we have a way of controlling the resistance in a circuit, we can therefore control the current through that circuit for a given voltage. And a device that does that is known as a rheostat or a potentiometer. And this is how your light dimmer switches work. If you have a switch at home where you kind of move a little dial or something so that you can make your lights brighter or dimmer, all you're doing is changing the resistance in that circuit so that you change the amount of current flowing, and therefore. When do your light bulbs burn out? What are you doing when your light bulb burns out? That's what happens, but when does it happen? Right, because the little filament's broken in there. But what have you usually done? It usually happens right when you turn the light on, right? So think about that for a second. Rarely are you just sitting there enjoying yourself, reading your book, and the light goes poof. Occasionally that happens, but it's rare. Usually you flip the light switch on, and the light burns out. What is the difference? What is the difference between a light bulb that isn't turned on compared to one that is turned on? What's the main change that happens? But let's think about just basic something that you would experience. What's the difference between an off bulb and an on bulb? One's given light, one isn't. No, yeah, but that's not what I'm looking for. Would you stick your tongue on a light bulb that's been turned on for a while? Because it's what? It's really hot. I didn't hear you. Temperature. Okay? So think about this. When the light bulb is off, it's cooler, right? It turns out, just like we just talked about, things that are cool have lower resistance. So when you flip that light switch on, before it's heated up, you have very low resistance. What does that mean in terms of current? Has a lot of current. There's a surge of current that goes through your light bulb right when you turn it on until it's heated up. If there's any kind of weakness in that filament, it's going to snap and break. So the main reason I'm having you think about this and talk about this is because I want you to remember the idea of temperature. Temperature affects resistance for most objects, okay? Okay. Power is our last thing we need to talk about. We talked about it last year, last semester. What was our definition of power when we were dealing with mechanics? Work over time. The rate at which work gets done or the rate at which energy gets consumed, it is exactly the same when we deal with electricity. It is the rate at which work gets done or the rate at which energy gets used. We still measure it using watts, and a watt is a joule per second, okay? But in electricity, we're going to have a way to calculate the power, dealing with voltage and current. And it turns out to be a very simple equation, and here it is. P equals IV. The power that something is consuming is equal to the current through it times the voltage across it, or the potential difference across it, okay? That last little line, you don't necessarily have to write it down. I just wanted you to see how the units work out. Current is coulombs per second. Voltage is joules per coulomb. The coulombs cancel out. You're left with joules per second, and that is, in fact, a watt. So here we have our equation for the power in an electrical circuit. But we also had Ohm's law, which said that I equals V over R. So I can take this equation, right, and I can rearrange it to say that V equals IR. You guys with me so far? Watch this. We're going to get tricky. I'm going to take this now, okay? Okay? And I'm going to plug it in for V. You with me? Okay? So I can plug in IR for V, and what do I end up with? Another equation for power, which says P equals I squared times R. Excellent. I could also take this and plug it in for I. And then what would I get? V squared over R. So really there's three equations to calculate the power used by a circuit, depending on what you know. If you know current and voltage, you can use the first one. If you know current and resistance, you can use the second one. And if you know voltage and resistance, you can use the third one. Done? Let's just kind of review. There's a flashlight. Great. Okay? Okay? So again, the purpose of, on and off switch is just opening the circuit or closing the circuit. And the purpose of electricity really is to transfer energy from one place to another to do work for us so we don't have to. Okay? In this case, we have chemical energy in the battery. I turn it on, I complete the circuit, electricity flows, and I take that chemical energy and I make light out of it so I don't have to build a fire. Okay, that's the whole idea. Now, if this is a 1.5 volt battery, let's say my light bulb has a resistance of 3 ohms. Okay, let's calculate the current in that circuit. Please tell me what the current is in that circuit. Okay, I equals V over R. Voltage is 1.5 volts. R is 3. Therefore, 0.5. What's our unit? Amps. Now that we've done that, please calculate the rate at which this thing is consuming power. What's the power rating of this particular flashlight? How many watts is it using? And why did you say that? What's that? P equals IV. We just calculated I to be 0.5, and we know that V is 1.5. So that gives us a power consumption of 0.75, is that right? Yeah. 0.75 what? Watts. Could we have done it using either of the other equations? Totally. And if you're feeling excited about it, which I can tell you guys are feeling excited, you should try it. See if you get the same answer, just for fun. So this is where we started. This is where we began. Can you define current? I think you can. Can you define resistance? I think you can. Hey, look, here's the equation for the resistance. Now you know what that means. Ohm's law. State Ohm's law. I equals V over R. Okay? Compare ohmic and non-ohmic behavior. We didn't do that. We didn't do that. Derive and apply the expression for electrical power. We did power. Solve problems. Hopefully you can. Last slide, and I don't have to talk at you anymore because now you get to actually think a little bit. Try these problems because you guys have done so much good listening. Let's see if you can actually apply it now. Okay? These are not super challenging. Let's see what you can do. Okay. Okay. How do you do the second one? P equals IV. P equals IV. And what do we get? 24 what? Watts. Excellent. How do you do the third A? 3A. Tell me the equation you're using. P equals IV? Yeah. Okay. P equals IV, and what do you get? 10.4 what? Everybody in agreement there? 10.4 amps? And then how do you do the last one? Energy. What is energy measured in? Joules. What? Watts or joules per second. So we know we're using 2,500 joules per second. Figure out how many seconds are 2 hours. Okay? And therefore, what do you end up with? 10 to the 7th. So 100, or no, what is that? That's 18 million joules. Okay?